Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on Laplace transformation, lecture number 1, which will include some basic fundamentals related to Laplace transformation, and then we will define Laplace transformation and existence of Laplace transformation and some problems. First basic idea is piecewise continuous function. Firstly, we define piecewise continuous function. A function is said to be piecewise continuous on an closed interval AB if the interval can be broken into finitely many subintervals, number 1. Number 2, the function is continuous on each subintervals except possibly at endpoints of each subintervals. That means the closed interval is AB. If we divide this closed interval into finitely many subintervals, let this is C, D, E, F, G and so on. The function is continuous on each subinterval. First subinterval is AC, second subinterval is CD, and so on. Function is continuous in subinterval AC except possibly at the points A and C. It is continuous. That means function is continuous in open interval AC, open interval CD, open interval DE, open interval EF, open interval FG, and so on. It may be possible that at endpoints A, C, D, E, F, G, it may be continuous or may not be continuous. This type of function is said to be piecewise continuous function. By an example, we shall explain this idea. Let us take an example. Function of t equal to 0 in the open interval 0 to 1, that is t greater than 0 and less than 1. Value of function is 1 on open interval 1 to 2, and value of the function is 0 in the open interval 2, 3. Here we see that, let here 0, 1, 2 and 3. If we take any point, any arbitrary point A between 0 and 1, then we will get f a minus h, limit h tends to 0. This is a minus h, means between 0 and 1. A remains between 0 and 1. A minus h also remains between 0 and 1. So value of the function will be 0. Limit h tends to 0, f a plus h, f a plus h, just after a. But this point also, a plus h point also lies between 0 and 1. So value of the function will be 0. And fa equal to this point also lies between 0 and 1. So this will be 0. So limit h tends to 0, f a minus h equal to f a equal to limit h tends to 0, f a plus h. So f is continuous at the point A. As point A is in the open interval 0, 1, A belongs to 0, 1. Now we take value of the function less than 1 and greater than 1. F 1 minus h, limit h tends to 0, equal to 1 minus h. That point lies between 0 and 1. So value of the function will be 0. Limit h tends to 0, f 1 plus h. 1 plus h lies between 1 and 2. So value of the function will be 1. So limit h tends to 0, f 1 minus h not equal to limit h tends to 0, f 1 plus h. So function is discontinuous at the point 1. In the similar way, we may show that any point between 1 and 2, the function is continuous. At the point 2, function is discontinuous. Any point between 2 and 3, the function is continuous. So at each open interval 0, 1, 1, 2, 2, 3, the function is continuous. But at the point 1, 2, 3, the function is discontinuous. So the function is said to be piecewise continuous. Our next concept is function of exponential order. We define this. A function ft is said to be exponential order alpha as t tends to infinity if there exists a positive constant. That constant is real number m. There exists a number alpha and a finite number t0 such that modulus of ft less than m e to the power alpha t for all t greater than equal to t0. If we take e to the power alpha t left side, then we get mod of ft e to the power minus alpha t less than m for all t greater than equal to t0. This type of function is called function of exponential order. Our third concept is function of class A. A function ft which is piecewise continuous on every finite interval in the range t greater than equal to 0 and is of exponential order as t tends to infinity is known as a function of class A. That is, function must be piecewise continuous and is of exponential order. Both two properties should be with the function, then that function will be called a function of class A. Now we define integral transformation. What is integral transformation? Let kpt be a function of two variables p and t, where p is a parameter that may be real or complex but independent of t, and the function fp is defined by the integral fp equal to small fp equal to integration limit minus infinity to infinity kpt ft dt. Here originally function is ft, capital Ft. We have given another function kpt and we have integrated this such that this integral is convergent because it is an improper integral as the limits are minus infinity to infinity. So we must have convergency property, otherwise integral is not valid. Then the function fp, small fp, is called the integral transformation of the function capital Ft. The function kpt is called kernel of the transformation. Some author use s in place of p and the transformation is written as fs. Parameter is taken s in place of p, but meaning is the same. So this type of transformation is called integral transformation of the function ft. Now we define Laplace transformation. Laplace transformation is a particular type of integral transformation. So firstly we have to define integral transformation. As integral transformation of the function ft is small fp equal to integration minus infinity to infinity kpt ft dt, where kpt is the kernel. If the kernel kpt is defined as kpt equal to 0 for t less than 0 and kpt equal to e to the power minus pt for t greater than equal to 0, then fp equal to we may divide this integral in two parts, minus infinity to 0 kpt ft dt plus 0 to infinity kpt ft dt. Here variable is t. So value of t between minus infinity to 0, that is less than 0. At that situation value of kpt is 0. So we write here minus infinity to 0, 0 into ft dt plus between 0 to infinity value of t, that is t greater than equal to 0. At that time value of kpt is e to the power minus pt. So here we write kpt equal to e to the power minus pt ft dt. So first term is 0 plus 0 to infinity e to the power minus pt ft dt. So here fp equal to 0 to infinity e to the power minus pt ft dt. This transformation is known as Laplace transformation. We may write this transformation as this is the transformation of the function ft. So we may write LFT equal to fp, that is LFT equal to 0 to infinity e to the power minus pt ft dt. This is the formula for Laplace transformation. We want to find Laplace transformation of the any function. We firstly write the function ft, then we multiply it with e to the power minus pt, and we take integration 0 to infinity and dt here. Sometimes some authors use s in place of p. So in that case they write fs here e to the power minus st. So we have to know that p and s, whatever be parameter, we get the same value. Now we prove the linearity property of Laplace transformation. Let f1t and f2t be two functions of t. So we will have two linear property as L a f1t plus b f2t equal to a L f1t plus b L f2t. This is the linear property. We shall have to prove this. We take left side L a f1t plus b f2t. We know Laplace transformation 0 to infinity e to the power minus pt. Now function a f1t plus b f2t, then dt. The Laplace transformation. So we will get 0 to infinity a e to the power minus pt f1t plus b e to the power minus pt f2t dt. We may divide into integration a e to the power minus pt f1t dt plus integration 0 to infinity b e to the power minus pt f2t dt. This a comes out a 0 to infinity e to the power minus pt f1t dt plus b 0 to infinity e to the power minus pt f2t dt. And this is the Laplace transformation of f1t. So we write L f1t plus b. This is the Laplace transformation of f2t. L f2t. This equal to right side. Hence proved. Laplace transformation is a linear transformation. Now we shall verify that the existence of Laplace transformation. That means in which condition the Laplace transformation of a function exists. The statement is that if ft is a function of t which is piecewise continuous on every finite interval in the range t greater than equal to 0 and satisfies mod ft less than equal to m e to the power at for t greater than equal to 0 for some constants a and m. That means the function is piecewise continuous and is of exponential order. That is, the function must be a function of class A. Then Laplace transformation of ft exists for all p greater than a. Now we will verify this. Since the formula for Laplace transformation of a function ft is L ft 0 to infinity e to the power minus pt ft dt. We divide this integral in two parts, 0 to t naught. T naught is a finite quantity, e to the power minus pt ft dt plus t naught to infinity e to the power minus pt ft dt. We write first integral by I1, this is I2. And in limit of the integration is 0 to t naught. T naught is a finite quantity. So I1 is a finite quantity, integration of this. So I1 is finite, this is number 1. Since I1 equal to a finite quantity. Now we examine the character of I2. I2 equal to t naught to infinity e to the power minus pt ft dt implies that mod of I2 modulus equal to modulus of integration limit t naught to infinity e to the power minus pt ft dt. If this modulus enter inside the integration, then that will be greater than equal to t0 to t naught to infinity. We get modulus of e to the power minus pt and ft. And the value of e to the power minus pt is always non-negative. Any value of e to the power something is non-negative. So we may write this as e to the power minus pt and modulus of ft dt. As ft is of exponential order a, so we may write t naught to infinity e to the power minus pt, this is m e to the power at dt, as m e to the power at is greater than mod ft. So we may write I2 greater than equal to T naught to infinity e to the power minus P minus A T dt. Now integration of this is e to the power minus P minus A T by minus P minus A, limit T naught to infinity. This will be equal to minus 1 by P minus A limit T tends to infinity e to the power minus P minus AT minus e to the power minus P minus A T naught to minus 1 by P minus A limit T tends to infinity 1 by e to the power P minus A T minus 1 by e to the power P minus A T naught. Equal to minus 1 by P minus A. This will be 0, 1 by infinity for P greater than A. If P greater than A, then this is positive and infinity, then e to the power infinity, 1 by e to the power infinity is 0. So this is 0 minus 1 by e to the power P minus A T naught for P greater than A. Already it is given in the statement P greater than A. So this will be equal to 1 by P minus A 1 by e to the power P minus A T naught. This is a finite quantity. Value of T naught is finite. These are all finite quantities. So it is a finite quantity. So modulus of T is finite quantity, less than finite quantity, then I2 is finite. Already we have obtained that I1 is finite. I1 is finite. So LFT equal to I1 plus I2 means finite quantity plus finite quantity equal to a finite quantity. So Laplace transformation is a finite quantity. So Laplace transformation exists under given conditions. The given condition is the function must be piecewise continuous and is of exponential order. That is, function must be a member of class A. In that case, with p greater than A, the Laplace transformation exists. Now we shall solve a problem of Laplace transformation. As we know, the formula of Laplace transformation of ft is integration 0 to infinity e to the power minus pt ft dt. Here ft equal to 1, we put this value e to the power minus pt, this is 1 dt. So we integrate this, integration of e to the power minus pt is e to the power minus pt by minus p, limit 0 to infinity equal to minus 1 by p, limit t tends to infinity e to the power minus pt minus e to the power minus p into 0 equal to minus 1 by p, limit t tends to infinity 1 by e to the power pt minus 1. For p greater than 0, we get value of this equal to 0, as p is greater than 0 means positive, and t tends to infinity, so 1 by infinity equal to 0, minus 1 equal to 1 by p. This is the required value of Laplace transformation of ft equal to 1. Now we solve the second problem. Here function of t equal to e to the power at. We shall have to find the Laplace transformation of this function. As we know the formula, Lft equal to 0 to infinity e to the power minus pt ft dt. So we write 0 to infinity e to the power minus pt, ft is e to the power at dt equal to 0 to infinity e to the power minus p minus at dt. Integration of this is 1 by minus p minus a e to the power minus p minus at, limit 0 to infinity minus 1 by p minus a, we write limit t tends to infinity e to the power minus p minus a t minus e to the power minus p minus a 0 equal to minus 1 by p minus a. This is limit t tends to infinity 1 by e to the power p minus a t minus 1 e to the power 0. This is equal to minus 1 by p minus a. For p greater than a, this is positive and t tends to infinity. Then we get e to the power infinity. 1 by e to the power infinity is 0. So we write 0 minus 1 for p greater than a equal to 1 by p minus a. This is the required value for the Laplace transformation of ft equal to e to the power at. I would like to report you that I will deliver lecture 2 in which some more problems of Laplace transformation will be discussed. So you continue for watching my video. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my channel. Thank you.